Hello, my name is Heikki Linnakangas. I am going to talk about how we made Postgres serverless at Neon. Stay tuned if you want to hear how do cloud providers run services in behind the scenes. So let's talk about serverless Postgres. Um, Before we go into that, I'm gonna say a little bit about what is Neon. It's a startup that we founded in 2021, and the core idea of the company is that we provide Postgres as a cloud service. And the idea was that we will build a service offering from the ground up in a cloud native fashion, make it really nice to be to run that in the cloud. And some of the features we have, it's very developer friendly, branching. Um, People love it because it's easy to get started with. But really, the topic of today's talk is the fact that we made Postgres serverless, and it's the only serverless Postgres offering out there. So, what does it mean really for a service to be serverless? I mean, it can mean many different things for many different people, but kind of the common thing is that you have your application, which you maybe develop locally on your laptop, or maybe you already develop it in on a cloud provider in the cloud. But when it's time to deploy it, you just deploy it to the cloud out there, not to any particular server or any particular instance that's running, but just to the cloud in general. And the idea is that the cloud provider takes care of running the service when it's running, and you don't need to worry about is it up and running or not, or you don't need to administer it. The cloud provider takes care of all of that. So in a sense, the fact that it's serverless, it's more of a contract between you and the cloud provider. Normally, if you're just renting server hardware or instances or whatnot, you have to you still need to manage the instance and install the software and so forth. But when you are running a serverless service, the idea is that the cloud provider takes care of all of that for you, and you just deploy to the cloud. And the cloud provider is responsible for making sure that it's up and running, not you. So in a way, the serverless service, it's always kind of a lie. Like all software runs on servers, or you locally on a laptop. But anyway, like there's no such thing as a serverless service. There's always a server behind it. The point is that as a user of the service, you don't need to think about that. So from your point of view, you don't think about the servers behind it. You might not even know where are the servers physically running, or you can't access the servers necessarily. You just know that it's running out there somewhere. But for a cloud provider, there's definitely a lot of servers behind the scenes. And when you're trying to make a serverless service, you definitely need to have a fleet of servers to run them on. But the point is that it's up to you as a cloud provider to manage. Like you need to manage those servers. The end user doesn't need to care. So for a user, the difference between a service and the service is that a server is that you are thinking about the service, and it kind of feels like it's always out there. It's always running, whether even if the server is physically not running or you don't know where it is. But the service is kind of always there, and you can always access it whenever you feel like it. Maybe you have an endpoint address to connect to, or a public URL or something. It's always there when you need it, but behind the scenes, the cloud provider might not have anything particularly running at the time. But when you connect to it, something will spin up and run your code in a serverless fashion. Some characteristics: if a service is serverless, there's probably no stop or start operations. Like you don't need to worry about those things. There might be like an enable or disable, or you might have some different terms for that idea that it's running or not. But there is no such thing as shutting down or restarting or stopping the server or the service. There's also, ideally, in a serverless application, there's no concept of having to choose a size. Like capacity planning isn't really a thing. You don't need to tune it. Like when you deploy, it's just always there. And the cloud provider's responsibility is to make sure that there's enough servers running the service, depending on the load. If the load increases, you have more. If the load decreases, then it can be scaled down. Another aspect, of course, if the service is infinitely scalable, you still have to pay for it. So one important aspect of serverless services is that you are only paying for what you use. So some kind of consumption-based pricing, whether it's compute hours that you consumed or number of requests or number of IOs or whatever. But the point is that you only pay for the capacity, you only pay for the usage, not for the capacity that you could be using. So there's another concept besides serverless, which is stateless. When you're developing your application in a serverless fashion, it probably also means that you can't really have a local state in your application because there's no server to keep that state in. The cloud provider can always shut down the components and scale them up or down or move them around as they want. So an important part of making your application serverless is that you try to remove state as much as possible. Because if a component, like whether it's a web backend or function as a service or something, if it doesn't have any local state, then it's very easy to scale out. Like you can just have many instances of that running, as many as you need, and you can easily, like the cloud provider can easily shut them down and restart them as you need, based on the load. And often the database is kind of the last component on your application stack that has the state. Like all of these other components, if they need to store something, they will typically store it in the database or directly in cloud storage or something. But often the database is kind of the last piece of your application that needs to have a state. And it's kind of by design. Like a database, like by definition, has a lot of state. Like that's where all the data lives, and that's kind of the other thing where everything else pushes down their state, because they don't. If you want your application to otherwise be stateless, you would typically use the database to keep all the state, but that means that the database itself can't really be stateless. And that kind of brings us to Postgres. So what we are trying to do is to run Postgres in a serverless fashion, which means we kind of don't want Postgres to have that local state, just like any other stateless application, or we try to minimize that. And all of these other things that I mentioned, like the cloud provider, us, we need to be able to shut down instances. We need to be able to restart and move them around and scale them up and down, depending on the load. But that's a bit tricky with the database, and Postgres in particular. It's an old robust database. It's been around for a long time, but it was never really built that way, with serverless applications in mind. So Postgres has a very traditional architecture. It operates on its own local disk, like it has access to a local file system. Well, local, it could be a network volume somewhere else, but still Postgres kind of manages that volume and assumes that it's the only thing reading and writing from that volume. Which means that you can't easily just shut down a Postgres database and start it up again. Like you need to have that state somewhere. You need to keep the disk around. You can't easily scale out and have multiple Postgres nodes. There's those projects that try to do multi-master and such, but it's a bit tricky. If you want to have read replicas, it means you need to duplicate the data and set up replication, which again is a bit of a hassle. It's not like you can just easily spin up new instances as you need to. Also, Postgres relies on the write-ahead log for crash safety, point out recovery, which is very much state. Like that's something that's data. That's where all the important data lives. You need to keep that somewhere. Also, Postgres kind of assumes that it has full control of the single server machine. Now, what does that mean if that server machine can be resized up and down or scaled up and down, or maybe if you want to scale out the reads, how do you kind of make that work? Then there are some Postgres specific limitations with the caches that can be easily resized and number of connection handling, and I'm going to talk more about those. But these are kind of the problems that we have to deal with in order to make Postgres serverless. How do you create that illusion of serverless in a service like Postgres? So the key to that is the architecture of Neon. There are a few pieces to that. So first of all, there's the proxy, which intercepts all the connections that come in. Like you don't connect directly to Postgres in Neon. You always go through the proxy. There's a control plane. We run a Kubernetes cluster and storage. I'm going to get into more details of all of these pieces. But let's first look at what happens when you connect to a database in Neon. Like let's walk through that process. So when you connect, what the user gets, or what you get as a user of Neon, is just a connection URL, like a Postgres URL that you can connect to with pSQL or your application. But when you do that, what you actually opened, what actually intercepts the connection first is the proxy. So when you connect with pSQL or something, you actually connect to the proxy first, and the proxy looks at, like, performs the initial handshake. It then performs authentication based on the credentials that we store in the control plane. And notice that there's no Postgres involved yet. So this is all still happening within these multi-tenant services, the proxy and the control plane, but your database is not even running yet. The next step is, if Postgres wasn't already running, if your Postgres instance wasn't already running, then the control plane launches Postgres, and it attaches to your database that you actually want to connect to. And then finally, here we are. After that part, the Postgres instance is running. It's connected to the storage. At this point, the proxy forwards the connection to real Postgres, and after that, it just passes through the bytes between the original connection and Postgres. But it handles that initial handshake, and this is the kind of the capability. This is why we can shut down Postgres completely, but you still have the illusion that when you connect to that URL, the proxy will wake up Postgres again, and your end application doesn't know that Postgres wasn't actually running when you try to connect to that. I didn't talk much about the storage part yet, but this is actually a very key and important part of what makes this whole thing possible, the storage system. So the important thing, the thing that really makes all this work, is that we separated compute and storage in Neon. I mentioned that the database is often the last piece in an application stack that has the state, and kind of data has a lot of gravity. Like if you have a terabyte of data, you don't just easily shut it down and move it somewhere else. It has gravity. You can't easily move it around. So the way we made Postgres serverless is by kind of splitting Postgres into two parts, or actually, like, the storage part is we plug in at a pretty low level in Postgres. But the idea is that we kind of push the state and all of that data down to the separate storage service. And by doing that, Postgres becomes serverless and stateless. So now that we've pushed down the state and the actual data to a separate storage layer, we can launch Postgres nodes independently, and we can easily shut them down and start them up again, and very quickly, because the data doesn't need to move. Like, the data lives in the storage layer then, and that doesn't need to move around. So a few words about the storage system. So it's a multi-tenant service. The same storage nodes handle the data for multiple customers. I mean, they're highly isolated. You can't access other people's data, but it's a multi-tenant service, and that makes it very efficient. Like, we don't reserve a certain amount of resources or a certain amount of servers per database. It's all handled by the same processes, the same servers. It's open source. If you want to play with it yourself, go ahead. It's written in Rust. This was an important criteria when we started, because it is a multi-tenant service, and we really don't want to have, like, memory issues or bugs that would expose the data between different tenants. So the security and isolation is important. That was a big reason for that. Ultimately, our storage system is also not the final place where all the data lives. So we actually rely on cloud storage, like Amazon S3 or Azure Cloud Storage or Blob Storage, for the final durable store. So in a way, our storage system is also just a cache of what we store in the cloud storage system. It kind of works as the glue layer between Postgres and the cloud storage, object storage, to make it possible for Postgres to be serverless. So the storage system also replaces your traditional, like, WAL archive and backups. It's the thing that allows us to do copy and write branching. And an important feature, or interesting feature, is that the same storage layer, same storage system can serve multiple read-only replicas of the same Postgres database. So if you want to scale out your reads, you can have multiple Postgres nodes running, and they all speak to the same storage, and they all share the same data, without having to create multiple copies of your data. It's also the thing that if Postgres crashes or we shut it down, it's also the thing that allows it to spin up real quick again, because Postgres doesn't need to do while replay. The storage system does that for you. But from a Postgres' point of view, we plug in at a very low level. So where Postgres would normally read and write the local disk, that's where we plug in. And instead of reading from the local disk, you send the network request to the storage system, and the storage system gives you back an 8 kilobyte page. And this is what makes it possible for us to start and stop Postgres instances. So that's the storage part, and that's what allows us to make the rest of the system serverless. But there's some other complications. For us, I said that we are separating compute and storage. Just to be clear, the compute in our case is Postgres, and the storage is the storage system. But we run Postgres nodes in a Kubernetes cluster, and there's some complications in doing that as well. So the part of autoscaling compute, there's really two problems we're trying to solve. One is stopping and starting the instances. I kind of talked about that already. But also we would like Postgres to be able to scale up when there's a lot of demand, when there's high load on it, but also scale down when there isn't. And that gives you a lot of flexibility, and that kind of gives you that serverless illusion where you don't need to choose the size of your server beforehand. It will just scale up as needed and scale back down again when it's not needed. So a few words about the stopping and starting part. I mentioned we launch Postgres on demand when you connect to it. And we shut down after 5 minutes of inactivity. So if you don't run any queries for 5 minutes, we shut down again. But it's all transparent to the user, because when you connect to it again, we launch it up again. And when we started, we had roughly 5 seconds of cold start latency. So if it wasn't running, it took roughly 5 seconds to spin up a new Kubernetes pod with Postgres in it, connect it to all the right services, and finally connect the original client connection to that instance. Back then we got a lot of feedback like, man, Neon is awesome, but the cold start latency, that's so bad. Like that, you really got to fix that. And we had customers asking for, I want to pay you so that you don't shut down your database, because I don't want to have that 5-second delay. So we were able to get that down to under 1 second, mainly by keeping a pool of like pre-warmed VMs with Postgres already installed and ready to go. And that kind of solved the problem. Like we don't hear that complaint anymore about the cold start latencies. That 1 second or I think it's around 700 or 800 milliseconds, that's good enough. People seem to be happy with that now. But the big part of what we do is maintain this pool of Postgres instances and keeping at the right size. I have a graph here about the workload on one particular region, and you can kind of see it going up and down based on the time of the day. But you can also see these interesting spikes. There's apparently a lot of people who have some workloads that run once per hour at the hour, and you can see those spikes here, which is really interesting, I think. So if you're developing an application out there and you have something that needs to run once per hour, please don't make it run at the hour. Make it run 5 minutes or 7 minutes or some random delay afterwards, so you don't hit that same spike as everything else. The other important thing about resizing or autoscaling the computes is being able to resize the VM instance based on the load. So we have a custom Kubernetes scheduler that allows us to do that. Like we wrote that, and there's a lot of complexity in allowing us to do that. But we can basically hot plug CPUs and memory into the running VM on the fly based on the load. There are some interesting challenges with this, and this is not something that we have fully solved, to be honest. So if there's someone, looking for the topic for a PhD or something, I think this would be a great one. The question is, when would you like to add more memory to your server? And there's kind of a few different answers to that. First of all, if the server is otherwise going to run out of memory, then maybe you should add more memory. That's option A here, and we do that. But it's also not very satisfying. What if you have a runaway query that is going to consume all of your memory anyway? Does it still make sense to kind of expand all the way up and then run out of memory anyway? Maybe not. But the more interesting problem is that there are a lot of queries that could potentially run faster if you had more memory because of cache. So what if you have 10 gigabytes of cache available and you're doing a lot of IO, but if you had 20 gigabytes of cache available, maybe your database or the working set would fit completely in cache and it would just go a lot faster. You don't really get an out of memory error in that case, but clearly more memory would be beneficial. The kind of case C here is that it also affects the planner. Like if the planner knows that you have a lot of memory available to do hash joins or something, it might choose a different plan to begin with, knowing that you have the memory available. And would you like to use that memory then to make your queries go faster? But it means you're maybe paying more for that. I don't know. Like that depends on your application. It's kind of tricky. One challenge is that Postgres doesn't easily scale up and down like that. You can't easily change the size of the buffer cache. So we implemented a second level cache that we can resize. There are interesting patches on Hackers at the moment to actually do this. So hopefully we'll get this in the future release. But for now, we are relying on the second level of cache for that. Another interesting question is, what is the right size for the cache? What is the working set of an application and over what period of time? We had one interesting customer who had a large database, and they had like our autoscaling algorithm looks at the 1 hour interval. Like how many pages have you accessed during the last hour? And then it kind of tries to choose the memory size based on that, so that 1 hour working set would fit in RAM. But this particular customer had an application that was doing a lot of random IO doing normal, like an OLTP application, and it wouldn't benefit from a lot of cache because it didn't fit in cache anyway. But once per hour, they had a batch job that actually accessed a lot of databases, like it scanned through some big tables, and we have this interesting pattern where our autoscaling would scale up when the batch job starts, and it would populate the cache, but it wouldn't actually reuse much of that cache, so it didn't give you much benefit while the batch job was running. But then, because it was set at the same 1 hour interval and they ran that batch job roughly once per hour, just before the batch job ran again and would actually use those pages that were cached, we shrunk the VM again. So we shrank it just before it would have been useful because of that. So we have to do some manual tuning for that particular customer. But this is kind of an interesting case. Like, how would you like the cache to be tuned? Would you like to account for these kind of batch jobs that run once per hour to make sure that they're cached? Or would you rather actually shrink more aggressively and save on resources and money, but then pay the penalty once per hour? I don't know what the right answer is. We're kind of still trying to figure out this, like what is the most general solution to this. Another topic is connection management. So Postgres doesn't do as well as some other databases with connections, to be honest. Like by default, we set max connections to 100 in Postgres, which is not a lot. Like if you have an application with lots of servers and you can easily hit that 100 connection limit. You can raise that. You can raise it up to a few thousand, but then you start to get other problems if you actually try to use all of those connections at the same time. So everyone who has administered a Postgres database kind of knows that you need to have a connection pooler to solve this problem. We also run pgvector because of that. But this is something we ran into early on and kind of had to solve. So the solution is to run a connection pooler. But from a serverless point of view, the connection state is a bit annoying actually, because a connection has a lot of state, so it's not exactly stateless. But it works out fine in practice. Like pgvector supports these caches and prepared statements nowadays. Like this was something we ran into early on when we were starting, but that's been fixed in pgvector. But these other things that have state in a connection, like cursors or per connection settings, the serverless application doesn't actually use these features. Like no one running a serverless application wants to use cursors or like long running queries. They just want to run one small query and get the result back and kind of treat each query separately. In fact, a lot of our customers were asking, like, I don't want to deal with these connections. Can't you just provide us an HTTP endpoint, like a REST endpoint to run queries? So we got this request a lot, and we actually then we implemented that. So we implemented a simple HTTP API in the proxy that you can connect to directly from your JavaScript application and just run individual queries, and the proxy will do the connection management for you in that case. So in summary, this is how we did it. The core of the whole system is the separation of compute and storage. Like, the storage system is crucial. It's what allows us to do all of these other things. But then there's all kind of heuristics and magic for resizing the VMs, doing live migration, and extra caching, pooling, like a laundry list of other small things. The HTTP API that kind of allow us to make Postgres into a serverless service. Thank you. If you want to play with it, go to neon.tech and play with it. Or if you have pSQL available, you can use pSQL to connect to Neon directly.